Hello, everybody. Welcome back. In this video, we're going to continue with our introduction to the vacuum technology for physics research, and I would like to speak a little bit more about the pumps. We've seen some of the principle of the pumping speed, the throughput, the conduction, and so on and so forth for the pumping, but we didn't actually speak about the pumps itself, the different type of pumps. And the second topic will be the quadrupole mass spectrometry. About the pumps, one thing that one needs to consider when it's necessary to reach a certain level of vacuum, which let's briefly recall it by medium vacuum. We mean something that goes from, let's say, 100 Pascal until zero point 0.1 Pascal. And with high vacuum, we think of something that goes from, let's say, 10 to the minus 1, 10 to the minus 5 Pascal, and ultra high vacuum, which is UHV, it's 10 to the minus 5, 10 to the minus 10 Pascal, okay? So one thing that one needs to remember is that it doesn't exist a pump that goes all the way. Of course, over here we have atmospheric pump, atmospheric pressure, which is 1325 Pascal, which is the atmospheric pressure. And there is no pump that can let us go in a single way from atmospheric pressure till the ultra high vacuum. What we need to do is to use a collection of pumps, two or more pumps, because the pumps working well in different pumps working well in different regimes. If we would like to categorize the pumps, we can say that there is a very first category, which is a throughput pumps, in which the working principle is that they drag gases, air, whatever is contained in the container, whatever gas is in there, and take it outside in a place where the pressure is higher, so to reduce the pressure inside. And the second category is what is referred as a getter pumps, okay? Sorry, getter pumps. Okay. If one has seen the previous video, we introduced the part on the chemisorption and physisorption, which are related to the absorption of a gases by a surface, which is part of the surface gas interaction, which we discussed a little bit last time. So getter pumps somehow are specialized in this type of physical process of the absorption in particular. Whereas throughput pumps is related to the mechanical dragging of the air, of the gases from. So it's more related to the things that we've seen about the throughput, etc. But let's maybe start with one of the first category, which we can call rotary roughing pump. Okay. This pump can be sketched in this way. So we have a location in which we, let's say this way. Let me see if I can sketch it. We have some oil here. This is some oil. There is a valve here, which essentially can open and close. This is where it is connected to the chamber. So the gas comes from here inside, okay, which means that our container is somehow here, somewhere here. Inside this is a rotary roughing pump, so there is an asymmetric mechanism which is composed by two springs which are keeping, as to say, compressed this part as it rotates. So it's rotate in a clockwise way. So the gas comes inside here, okay? And when this part is coming this way and this one is going this way, it's essentially compressing all the way the gases until its exposure here. It goes, this red valve opens, the gas which is compressed by the rotation of this mechanism goes inside here, and then it's evacuated. Okay, so this is the basic principle of this pump. This type of pumps can work well in a regime, as to say, which is starting from the atmospherical pressure, okay? So starting from, let's say, the initial pressure is 10 to the 5 Pascal, as to say, and the ultimate pressure, the final pressure, is somehow related to 1 Pascal. Often it's important to consider a parameter which is the compressive ratio, which is essentially the ratio between the inner and outer pressure. So in this case, is 10 to the 5. Okay, so it's the ratio between the two pressure, the one outside and the one inside. These type of pumps can reach a pumping speed of somehow 40 to 60 liter per second. That's highly depends on the cost of the pump, the dimension that we are considering. It's a very noisy pump, but it's pretty much okay because it's literally inexpensive. Its cost is very low, and it allows us to reach a certain, let's say, medium vacuum according to our classification. Somehow in the medium vacuum range, starting from the atmospheric pressure. One interesting things about this pump is that in the way I sketched it, we can call it ballastless, so there is no ballast. But what is ballast? Ballast is a gas that is required because, let's say, this is ballastless, and this is ballasted. Okay, but why do we need ballast? Because sometimes when this one is compressing the gas in this area, so imagine that this black one is rotating, so it's compressing these gases inside here. But if it's compressing too much, it will actually liquefies it. So there is a phase transition from fluid into a liquid form, and therefore it can spoil the oil, this blue oil here, and we need to change it often. So the way to solve this is to create a little valves here with some so-called ballast gases that essentially reduces or completely mitigated this liquefaction. Okay, so another type of this pump, of this throughput pumps, which is a mechanical one, it's maybe something that is like a piston pump. okay, in which we have like if you've ever seen a cylinder of an engine, it's something similar. So there is like a piston into a cylinder. Okay, so this piston, which is let's make it a different color, this blue one is essentially the piston, and this piston can goes up or down, and the gases is coming from here. When the piston is down, let's say in maybe in this position, is increasing, is filling all these gases, and when the piston goes back to the position that I draw on this one, it evacuates the gases from here. So it's a very rough and imprecise way of making vacuum. It can still consider that we can have the same performance as the rotary roughing pumps, plus or minus, but it's also inexpensive. Another way of doing this, a little bit more efficient, is the root pumps. Well, the root pumps is somewhat difficult to draw. It's like 1/8 here, with another one placed in this way. They are all inserted inside a mechanism like this, and they are simultaneously rotating. Maybe my drawing is not perfect, but the idea is that there are different phases in which the gases, which is coming from here, so let's say the gases is coming in and it's going out maybe here, okay. Sorry, so our chamber, our vessel is on the green part, and the higher pressure is here. Okay, and the way in which this principle works is that by rotating in a specific way, they can pass the gas and compress it from one part, from the left to the right. So this one works from a little bit more range, as to say. Let's say that if we keep this parameter, maybe we can say that it can reach maybe 10 to the minus 2 or so Pascal, okay? So we can also update the compressive ratio. Okay, so this is one way to get to some, as we say, medium pressure. If we would like to go to an higher pressure, something that can reach a very, very high pressure from the same category of the throughput pump, we can consider another one, which is called turbo molecular pumps, which is very efficient way of pumping. Essentially, there is a stator. Of course, these are just sketches. It's gonna be too difficult for me to draw precisely the behavior of the pumps, so I will just give you some idea of the physical principle of some of such pumps. But if you want more details about this, you can either search on Google or just let me know in the comments. I can give you some information more on the pumps if you're interested in. Essentially, this type of pump, turbomolecular pumps, is very, very, very efficient way. It's composed by a stator, which is this part here, which it stands still. It's rotating, but it's rotating without moving. Whereas these blades that the pictures here with some orientation angle are just blades that are rotating. Okay. if you ever seen a turbine or a fan, is similar. If you want to have something in your mind to think about it, think as a fan, and this fan is rotating very fast with a rotation of 60,000 cycle per minute. Okay, so rotating very very fast. And the physical principle of obtaining the pressure is by momentum transfer, because the gases that are coming, I think we use the yellow one. The gases that are coming from here will passes through the blades, okay, and we actually create a flux. Okay, we create a flux of gas that goes outside in the bottom part of the turbomolecular pumps, and the particles that they are eager to come back. Okay, they will meet the blades, which are rotating faster, as I said, and they are pushed back from where they came. So very very few molecular gases can go back to the chamber, to the vessel. Most of them will instead be dragged down with a flux which I shown as red arrows that goes downwards. So this type of pumps have an initial pressure which has to be somehow very low. So sometimes from somewhere between the medium vacuum regime, but they can reach very 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 low pressure, maybe 10 to the 9 Pascal or so, and using a pumping speed which goes from 40, let's say, to 100 or even more liter per second. These parameters highly depend on the dimension, on the cost, on the brand of these pumps. Those are just indicative numbers, just to give you an idea of how we can do. So just what we have seen so far, we can think about using maybe a rotary pump in combination with a turbomolecular pumps to go all the way from atmospheric pressure down to the ultra high vacuum or so. Okay, so we need two pumps. Okay, one that works well in a regime from atmospheric to medium vacuum, and the other one turbomolecular, which work well from the medium vacuum into the ultimate pressure of ultra high vacuum or high vacuum. Okay, so I think we can pass through the second category of pumps, which, as I said, is getter type pumps. And these getter type pumps work with the principle of gas surface interaction. In particular, there will be some two different way of these getter pumps. We can have evaporable, sorry, vapor, or non-evaporable pump. Okay. Let's start with, or sometimes is ion getter pumps. Ion getter pumps. Okay. So let's start with the evaporable pump. Evaporable pump. So in this type of pumps, we should bear in mind that, as I anticipated in the last video, the first video, this type of pumps work with the gas surface interaction. No? So we want our gas to reach the surface. And that's why it's important to it was important to discuss the mean free path, because the mean free path is the distance between two collision events between the gases molecule, and so we will need a certain mean-free path in order to allow the gases to effectively reach the surface and works well with this principle. So in this evaporable pump, we have a filament inside, which can be made by titanium, which is connected to a certain bias, okay, and we let the gases from the vacuum from the chamber come from this way. So where I put the dot is where the chamber is. Here we need some barrier, some protective barrier. Why? Because the gases that is released by these titanium ions, we do not want it to get dispersed. It needs to be stay inside this material. So essentially, the working principle is that by applying a different of potential, we will create a current. The current will increase the temperature of the filament, which will sublime, passes phase transition from the solid into the gases, and it will release ion of titans that will essentially create a cover, okay, onto which is spanning the surface of the interior of the pump, and this cover will make the atoms of the molecules become trapped, become absorbed by the surface, and in this way they will be effectively reducing the gases by absorbing and keep it inside the pump. Of course, this will form a first layer, then it will recover another layer, and so on and so forth. So, as you can imagine, this type of pumps requires an initial pressure which has to be somehow in the medium vacuum regime. Otherwise, we will fill up if the pressure is higher. There are a lot of molecules of gases which will essentially saturated immediately the surface. So that's why we need a medium vacuum, but we can reach pretty much a high vacuum regime with this pump. 10 to the 5, I would say 10 to the 6, 10 to the minus 6 Pascal. With a pumping speed which is somehow very high, okay? Maybe not 40, but from, let's say, 10 to also 1000 liter per second. Okay. I just remember that I didn't talk about another type of pumps, which is essentially very good type of pumping. There is, let me sketch it in this way for you. There is let's call a heater. Okay, on top of this heater there is a container which has some oil container, and the oil goes inside a pipe. Okay, all the system is composed is inside a vessel which has a cooling. I don't remember if there is a cooling here. I need to check. But in any case, in this one, there is a cooling system which keeps the surface very cold. So the heater increases the temperature of the oil, which will evaporate and goes in a flux with very high speed all the way up into this chimney until it reaches the surface where there is some nozzles. So the oil will be sprayed with very high momentum, okay? towards the side. So what happens is that we have our chamber where we want to reduce the pressure here. So as usual, the gases that are coming from the vessel, it's in green. What happens is that this molecule, this ion, will be eventually heated by the oil molecule of the with high momentum, and they will take it onto the surface. The surface very cold, and essentially they will become liquid by the cooling effect, and they drops down. Okay, so they drops down. So this is the working principle. The pumping speed, even in this case, is very high. It's almost 600 liter per second or so. And again, it will need to be starting from, I would say, medium vacuum, but it can reach high vacuum. Okay. It can reach high vacuum with a compressive ratio of 10 to the 5. Okay, so I was discussing the vapor pumps. Maybe it's worth to discuss about the ion getter pumps. Let's say ion getter pumps. Okay, this type of pumps is composed by an anodic part and a cathodic part. The anode is essentially an honeycomb-like structure. Okay, something like that. Okay, honeycomb. The cathode instead is a plate, which is here, and there is also one here. Okay, so the blue one is the cathode, and the black honeycomb-like structure is the anode. There is also a magnetic field, which is pointing in this direction, something like, I would say 1500 Gauss, something like that. And if we make a cross-section of these ion getter pumps, I want to make a cross-section, what I will see is something like this. Okay, I don't know what is this one. Okay, we have the anodic part, which looks like this. We have said that there is an external magnetic field, and whereas the cathodic part, let's say something like this. Okay, this is the cathode. And this is the anode. Okay, the gases maybe is coming from here. Okay, from the chamber. And remember that this type of pumps keeps the residual gases inside of it, so it does not evacuate it, so the gas goes in and never goes out. And but as it comes inside, we will have neutral atoms. We will have some maybe some ions. We will have maybe free electrons. We will have different types of particles inside the molecules, and by the effect of the magnetic field, what we have is that the electrons becomes to spiral, okay, toward the direction in which the magnetic field is pointing, and eventually they will hit a neutral particles, a neutral atom or molecule, and they ionize it, and so also the ion itself will be spiraling. This one becomes ionized and spiral again. So essentially the principle is that they are pushed towards the cathodic part. As soon as they reach the cathodic part, they pulverized the cathodic part. The cathode is made again by titanium, and the titanium will be spreaded and fill up all the surface that there is, anode and cathode, and these ions trapped will be trapped by the surface, as I described previously, where it will be absorbed by the surface. And in this way, we will have a pulverization of the cathode. Sorry, so we will have something that becomes like this. So the material will be left over, and we will have an increasing of the dimension of the anode part. Okay, because there will be all the residue gases, ions attached to it. So this is the working principle of the ion getter pumps. Again, I would say that they will share the same pressure. We need to start with a very low medium to medium pressure, and they can reach higher ultra high vacuum. There is also another one which I didn't mention earlier, which can be the cryopump. Okay, cryopump, cryogenic pump are essentially a container which is immersed by a very low temperature liquid, almost close to the absolute zero. Inside there is a spongeous material, and the gases comes from here and essentially are trapped in this porous sponge-like material. And this type of pumps require high vacuum, but it can reach ultra high vacuum. So the initial pressure will be 10 to the, let's say, minus 8 Pascal, and the ultimate pressure is 10 to the minus 10. So to reach effectively the ultra high vacuum, we can use cryogenic pump, which has very low compressive ratio, but essentially they work well only in this region. Okay, so one side topic is how do we actually measure the pressure inside a container? Because last time we've seen that it's related to the pressure is somehow related to the arrival rate, which is the number of particles that are hitting a surface, okay, in a given time. We've seen this is the number of particles divided by the surface divided by time, okay. The pressure is related, is proportional to this arrival rate, okay. But how do we measure it if in this case? So there are quite a few techniques. Vacuumeters are called. One can use some mechanical, let's say, bending of a membrane. So we have like a membrane which is stretched like this blue one. High vacuum is in this direction, so this will bend over the membrane, and with some measurement devices we can essentially understand what would be the pressure by measuring the deflection of such membrane. We can indirectly measure the pressure. Some other method are considering to have inside the container a filament which has a known behavior according to the pressure, maybe in terms of conductivity, thermal conductivity, and by measuring the thermal conductivity difference we can evaluate what will be the pressure inside, again indirectly, and so on. And but sometimes knowing the pressure is not all. in some experiments, we might need to know what type of residue gases there is inside the container. So it's not a matter of only pressure. Also, we want to know what type of gas is still present into the chamber. Because maybe it's an aggressive gases or it has some potential interference with the sample or so on. So a technique which is used to determine what type of residue gases there is called quadrupole mass spectrometry. In which we essentially are able to collect ions from inside the chamber and classifying it according to their specific mass to charge ratio. Okay, in a way which I'm going to explain in a second. So the core of this system, the core of this system is composed by 4-cylinder. 4-cylinder, like this, which has a distance r naught, roughly 3 millimeters, say, from the center. They are connected with direct and radio frequency potential, equal in magnitude but different in sign, opposite to each other. So essentially there is a potential which is a quadratic form of the potential, which we can think about something u plus v cos omega t x squared minus y squared divided by r naught. Okay. Okay, so what is the sketch is the principle of working. So we have our vacuum. We have an ionizer, which essentially ionized by electric. Maybe we can have electric bombardment by thermoionic emission of the electrons, which will ionize the molecule of the gases, and once it has been ionized, they will be making passes through this quadrupole, as I show. So this is the quadrupole for the 4-cylinder, and the ion goes inside, and if it will reach the other side, and I will explain why there is an if, there is a detector which collect the ion, and whenever it has a sufficient collection, it will measure a current, and so it's able to determine what type of ions have crosses from the ionizer into the detector. So I said that there is this type of potential. If we look about this potential, we see immediately that if, for example, we consider that this is the z direction, whereas this is maybe x and y direction. In the z direction, the potential itself, this phi, does not depend on z. And also, there is also a cylindrical symmetry, because if x is equal to y, we see that this phi is equal to 0. Okay. So if one wants to write down the equation of motion, the three different equation of motion in the three coordinates that we have, of course we have mz dot dot. With double dot, I mean the dot means derivative with respect of time, as always. Is equal to 0. Let's say if we do x dot dot plus again we need to specify 2e okay, u plus v cos omega t, say x over r naught is equal to 0, and my dot minus, because we said that it has a different sign, u plus v cos omega t, and it goes with y divided by r naught is equal to 0. Okay, so this is the equations which are discipline the trajectories of the ions, okay, and they are written in this coordinate system x and y and z. We can see immediately from this one, from the z one, that if we integrate it, we have z dot is equal to a constant. So the ion itself, as they are crossing this cylinder, as they are crossing, they will have it constant speed in the z direction. Okay, so in this direction, the speed will be constant, like of the ion. It's worth to introduce a different type of coordinates, which is a q, which is for EV divided by m r naught squared and the frequency squared, and alpha, which is 8 EU. So alpha depends on the u, and q depends on the v, and it has the same denominator. Okay. Omega t is 2 phi, and f is equal to omega divided by 2. With all of this coordinates, we can rewrite the set of equation above as an equation which goes under the name of Matthew or something like that equation, which is d squared of f d phi squared plus alpha plus 2q cos 2 phi f equal to 0. And so we are able to rewrite it for the two coordinates. We said that the z there is no need, but for the other two we have d squared x d phi squared plus what we have alpha plus 2q cos 2 phi x, we said, equal to 0, and d squared y d phi squared minus alpha plus 2q cos 2 phi y equal to 0. Okay, so this is the equations of motion. And essentially what is happening, the important part is that we have this, let me remake the drawing. Okay, and I will make it very nice for you. So hold on a second. Okay, not really perfect, but it's understandable. Okay, so we have the plus charge here and the minus charge here. The z direction is in this one. This is x and this is y. Okay, so let's see what happens in this cross section. Okay, so I essentially made a cross section of this one. Like I make a cross section here, and I'm looking it in the cross section. So this one is the cross section that I draw above, because I want to see what's happened to our ions as they are crossing these 4 rods. So let's focus on the x-axis first. So we will have an ions, which imagine that we are looking only in the x direction. So it will, according to his masses, it will be feeling the effect of the rods itself as they are crossing into the z direction. So we'll start oscillate, okay, this back and forth if we are just looking at the x direction. And if its mass is below a certain value, okay, it will that's considered as a smaller mass, so small mass in x direction, will progressively feel an increasing of the amplitude until they will hit the rod and discharge. Okay, so small mass in the x direction will experience an increasing of the amplitude of what? Of the oscillations in the x direction until discharge. Okay? Higher masses, on contrary, higher masses, ions, will feel a little bit less about this. They will maybe oscillate until here, but they are able to reach the detector, so they can cross it and reaching the detector. So high masses can reach the detector, which means that the x direction is high mass pass filter. Okay, makes sense? So in the other direction, in the y direction, it's exactly the opposite. Exactly the opposite, because if we have an ion here, if its mass is bigger, the amplitude will be losing stability immediately and they will hit the rod and discharge. So high ion mass in the y direction will become unstable and discharge. And of course, low ion mass will reach the detector. All right. So, of course, this occurs simultaneously. There will be spiraling. It's not something linear as a show. I just did it for drawing purposes, the projection into the x or y direction. But essentially, what one needs to remember is that it's according to the mass to charge ratio of the ions. The quadrupole mass spectrometry is capable of filtering the ions according to their mass to ratio and charge specific, and therefore we can identify what type of ions are crossing just by modifying what? By modifying the two potential which are determine which ions can process and which not. Often there is also some plots associated to this. The plots are like something like this, in which we have the Q and the alpha in the respectively in the x-axis and y-axis. We have like something like that, where maybe we can say that there is let's say something like inside here is called stability region. Stability region, whereas outside of this there is the unstable region. Okay, so each point in this plot represents a specific alpha and q coordinates. So if we imagine to send a line from the origin until the very top, okay, of this, we have reached a specific value, which is the highest alpha possible. And in this regard, if we tune down our potential in order to have alpha star, say Q star, we will have a very high sensitivity because only ions with that specific alpha star and Q star value can pass. But the resolution of this filter is absolute. It's essentially very close to zero because only that specific alpha and Q can passes. So on the contrary, if we set, for example, alpha 0 almost to 0, we will have a very flat curve here in which we have a resolution, the maximum resolution possible, which is all this, but we lack of understanding in the alpha direction. So the best will be a compromise in which we crosses somehow closer to the top, but we have we have high sensitivity, but essentially not only high sensitivity, we also have some resolution, okay, which is something like that, okay, some resolution, okay, in our measurement. Okay, so this pretty much concludes our introduction to vacuum technology. We have seen the basic principle of the gases entrapped, which have a different speed and velocity. We passed from the fluid dynamics, the throughput, the conductance, and then we introduced the concept of the pump from the pumping speed, the pumping equation, which is very useful to determine the time that is required to get specific vacuum, which can pass it from minutes to days. We've seen a set of different type of pumps, some of which work well in a specific pressure range, some other works well in another range, and eventually we've seen a technique which is the quadrupole mass spectrometry, which is used to determine what type of ions, what type of gases is still inside the chamber by ionizing it and making pass it through this quadrupole detector, which according to his specific mass to charge ratio let us understand what type of ion was inside. Okay, so thanks everybody, and let's meet again for the next video, which I'm not sure will be about the scanning electron microscope or the atomic force microscopy. I need to think about. One of the two will be the next video. Thank you, and have a good night.